Before I start, um, we have a single variable problem, right? In week three, we are looking into single variable optimization, right? So when we are looking in why are we do we can directly find differentiation of a function when there is single variable, right? So why do we have to go through this much of procedure? Like first we have to find the bounding area, then we have to apply any iteration method to find optimization. Why are we doing that? Any answers? Yeah, we can just simply find the differentiation and make it equal to 0 and find the x value, right? So why are we doing that is there are some functions for which we don't have a differentiation at every point. So suppose if I take a function mod x, you guys know how the mod x looks, and you know where the minimum of this function also exists. But using differentiation, can we find that optimization? Because d by dx of mod x is, sorry, so this part that this doesn't exist at x equal to 0, right? So we also know that at x equal to 0, the minimization of mod x exists. So that's why what we will do is when for functions which don't have derivative at each of the location, and if it is not continuous, so we go to this kind of methods where we can solve it and find the optimal. Okay, sometimes what will happen is when you are differentiating and you are trying to obtain, differentiating and making it equal to 0, it's very difficult to obtain the roots of the differentiation of the function as well. So that's why we use these kind of methods. Okay, so then, yeah. Uh, in last class, first, what we have discussed was we discussed about first bracketing methods like exhaustive search method and bounding phase method, right? So let's start with the problems related to it first. I'll just give one example for each of these methods. So first question is find the optimum for the function f of x equal to x square plus 54 by x. Take x naught equal to 0 0.7 and delta x equal to 0 0.5, and using bounding phase method, find out the lower and upper bounds of the problem. So how we will do that? Do you guys need 1 or 2 minutes to tell me the solution, or shall I start with the solution? Okay, I'll just wait for 1 minute and then I'll start. You can tell me the answer if you are doing it. The function is x square by plus 54 by x. And we have to take x naught equal to 0 0.7 and delta x equal to 0 0.5. So how the bounding phase method looks if we have a function like this. If x naught is here, first we will calculate x naught minus delta x and x naught plus delta x, and based on the because it's the function value is decreasing in this side. So delta is positive. Okay. And we have to keep going towards this side. Then this will become x naught, right? So we will keep doing this in the next title. Sorry. Then we will find x1 equal to x naught plus delta x. Then we will find if f of x naught is greater than f of x1. Then again we'll go with x2, that is equal to x naught plus 2 into delta x. Like that we will go, right? And similarly again we'll calculate if f of x1 is greater than f of x2. We'll keep going this iteration till the sign reverses. This is how bounding phase method looks. Okay. So I'll start the solution. You can tell me the answer in between as well if you have done the solution. So first what we are going to do is first x naught is equal to 0.7. X naught minus delta x is 0.2. X naught plus delta x is 1.2. Okay, I'm just using these values here. And first find f of x naught, that is equal to 0.7 whole square plus 54 by 0.7 is equal to 77.63. I've done all the computations, so that's why I'm writing the values uh, ahead so that we have time to discuss everything in this lecture. Then f of x naught minus delta x is equal to 0.2 whole square plus 54 by 0.2, that is 270.04. Then f of x naught plus delta x is 1.2 square plus 54 by 1.2 is equal to 46.44. So here we have f of x naught minus delta x is greater than f of x naught. Look at these values. 270 is greater than 77.63 is greater than 46.44 x naught plus delta x. So therefore, Lexar has used a notation x, a delta. So here I'm using delta x, okay? So delta x is positive. Why is it positive? Because sorry, the we are seeing that when we are moving this side, that is positive x-axis direction, we are seeing there is a decrease in the function. So minimum value exists in the positive direction of x. So that's why delta is positive. In that way, you just think, okay? So now we have to calculate xn plus 1 equal to xn plus 2 power n into delta x. So in the first case, what we are doing is x1 equal to 0.7 plus 2 power 0 into 2.5, that is equal to 1.2. Okay, this we have already computed f of, okay, so f of x1 is, f of x0 is greater than f of x1 here. Then f of x2 is 0.7 plus 2 power 1 into 0.5 is 1 point. You have to take 1.2 here. So it is 2.2. Then calculate f of x2. F of 2.2 equal to 2.2 whole square plus 54 by 2.2. Okay, so that value is equal to 29.38. And f of x1 is 46.44. So then here f of x2 is less than f of x1. Similarly, x3 will be 1.2, 2.2 plus 2 square. We are taking this 2 square into 0.5 is equal to 4.2. F of x3 is equal to 4.2 whole square plus 54 by 2 point, so 4.2 is equal to 30.4. Here we are seeing that f of x2 is less than f of x3 and f of x2 is also less than f of x1. Okay, I'll just write the values here. F of x1 is 46.44. This is 29.38 and 30.4. So we can see that the function is decreasing and then increasing between x1 and x3. So therefore, the solution lies between x1 comma x3, that is equal to 1.2 comma 4.2. Okay. So did everyone get this answer? Okay. Next, for the same function, what we will do is we will try to solve it using exhaustive search method. Okay, so the function is f of x equal to x square plus 54 by x, and the intervals are 1 less than or equal to x less than or equal to 11. So here we can see how different these two solutions also will, I mean, these two methods will give you the ranges also. Okay, so here we have n equal to 20. We can have 10 intervals. Okay, and we have to use exhaustive search method and find lower and upper bounds. You guys can try out for 1 minute, then I'll start the solution. If you are done with solution, you can tell me in between also when I'm doing the computation. So in exhaustive search method, what will happen is if they have given lower and upper bounds a comma b, we're trying to get smallest bracket from that. So first we will divide into n intervals, suppose. Then the each of the interval size will be b minus a by n. Okay. So first what we will do is this will be our x1 and then x2 equal to a plus delta x, x3 equal to a plus 2 delta x. And then we will see if that x1, f of x1 is greater than f of x2 is greater than f of x3. If we get this, then we have to move in this direction. We have to move in the minimization direction so that we can get this minimum. So after that, in second iteration, this is first iteration. In second iteration, what will happen is this part will become x1, then this will become x2, and then we have a x3, which equal to x2 plus delta x. So like that we'll do this iteration repeatedly till we have a condition f of x1 is greater than f of x2. This is less than f of x3. So you can see the function is decreasing, then increasing between x1 and x3. So this is our bounded bracketed area. So let me start with the solution. What we have is we have a equal to 1 and b equal to 11, and we have to divide this region into 20 intervals. So delta x will be b minus e by n, 11 minus 1 by 20 is equal to 0.5. Okay, delta x will be. So in the first iteration, x1 equal to a, that is equal to 1, x2 equal to x1 plus delta x, that is equal to 1.5, because x1 is 1 and delta x is 0.5. Then x3 is equal to x2 plus delta x. So again it is equal to 2. So first find the value of f of x1, that is equal to x1 square plus 54 by 1 is 55. F of x2 is 1.5 square plus 54 by 1.5, 38.25. F of x3 equal to 2 square plus 54 by 2 square is equal to 31. So if you see, f of x1 is greater than f of x2 is greater than f of x3. So if f of x1, x2, x3 are in this way, so we are going in this direction, right? So whenever, because we are working on unimodal functions, so if you don't have any clarity, you can just draw the graph, any random graph, and see how these values are arranged in that graph, okay? So that you will not be confused. So now second iteration, x1 will be equal to this value, then x2 will be 2, x3 is equal to x2 plus delta x, that's equal to 2.5. Again, we have to find f of x1 is 55, f of x2 is 38.25, f of, sorry, writing it wrong, that f of x1 is 38.25, okay, f of 2 is 31, and f of x3 is 2.5 square plus 54 by 2.5, that is equal to 27. So even here we are seeing that f of x1 is greater than f of x2 is greater than f of x3. So we have to go for next iteration. Third iteration. So in this case, this will become our x1. x1 equal to 2, x2 equal to 2.5, x3 equal to 2x2 plus delta x is equal to 3. So here f of x1 equal to 31, f of x2 equal to 27. These are already computed in previous iteration. So I'm just using those values directly. F of x3 is 3 square plus 54 by 3. Let's see. Sorry, this will be 27.8. Okay. This is equal to 27. So here also we are seeing f of x1 is greater than f of x2 is greater than f of x3. Then we have to go for fourth iteration. X1 equal to 2.5. This will become our x1, x2 equal to 3, x3 equal to 3.5 because it's x2 plus delta x. So f of x1 is 27.8, f of x2 is 3, sorry, 27, f of x3 is 3.5 square plus 54 by 3.5. That is equal to 27.67. So what is happening here? F of x1 is greater than f of x2, which is less than f of x3. So here if you see, first value is higher, decreasing and then increasing. Okay, so somewhere here we will have a minimum. So our search area will be reduced to x1 and x3. So search area 2.5 comma 3.5. So if you see this, here we are getting 2.5 by comma 3.5, and in previous method we got 1.2 comma 4.2. This is huge. I mean, there is a huge gap. I mean, the width is huge. But also if you see this 1.5 comma 3, 2.5 comma 3.5, it's lying within this region itself. So from both, we are getting like same kind of search area, but in the bounding phase, we are getting the width is large. Okay. So now what we will do is we will look into few of the conditions in region elimination method. I hope these two methods are clear. If you have any doubt, you can ask me. So conditions are first, if you have a minimization type unimodal function, this is A, this is B, and we have x1 is less than x2. So this is positive x direction. So I'll just color each of the conditions. X1, x1 and x2. So the first condition is f of x1 is greater than f of x2. Okay, so also you can see that the x2 can also be at this location also, right? If this is our x2, it will satisfy this condition also, and also f of x1 will be still greater than f of x2, right? So that's why when we are doing regional elimination, when f of x1 is greater than f of x2, we are for sure that we can eliminate this area. Is it clear why we are only eliminating this part? Because you might also think that, oh, sorry. Okay, yeah. If x1, x2, if you imagine x2 is here, we can also eliminate this area because from the graph we are clear minimum might be existing somewhere here between x1 and x2. But there is also a chance x2 can be here. So that's why we can only eliminate this a to x1 part. I hope this part is clear. And then what we will do is then we have one more condition, which is the second condition is f of x2 is greater than f of x1. This is in the is also it's the same condition if x1 is always less than x2 that we are considering. Okay, so then here, sorry. if the x2 is here, okay, then and x1 is here, it should satisfy. And same along with this, x1 can be here also. It will satisfy both the conditions that x1 is less than x2 and also f of x2 is greater than x1. F of x1, sorry. So in that case, what area we are sure that minimum won't be lying? We are sure the area won't be lying in this area. So eliminate x2 comma b. Okay. And then we have one more condition. Third condition, f of x1 is equal to f of x2. So this is simple. X1 is less than x2 and we have these function values same. Sorry. So we know we can. So from this graph, what is clear? We can eliminate this area and this area because minimum will be lying somewhere here. Okay, in between x1 and x2. Therefore, eliminate x1 comma x2. Sorry. So eliminate a comma x1 and x2 comma b region. Okay, in this case, search area will be x1 comma b. Here, search area will be a comma x2. And here, search area will be x1 comma x2. So if you have any questions like this, just draw a simple graph, unimodal graph, and then you can understand how the elimination is working.